So in this lecture video, I'm going to show how to actually solve the particle in a box quantum mechanics problem. And what you're going to see is that while we're solving the particle in a box problem, we're going to gain these things. We're going to gain the wave functions. In this case, they're going to be time independent and only dependent upon one space dimension. There's going to be quantum numbers. And what's interesting about the quantum numbers is the problem itself is going to give us whether or not we're talking about integers or half integers or even integers or odd integers or integers squared, right? So the problem is going to dictate the index, the quantum numbers. They're not necessarily always going to be just the counting numbers. Sometimes it could be that they are both positive and negative counting numbers, or they might be odd integers divided by 2. Like it sort of depends on your problem. The quantized energies are also going to come out of the solution. So when we solve Schrodinger's equation, we don't necessarily get normalized wave functions, but we're going to do that last. When we solve Schrodinger's equation, we're going to get quantum numbers, we're going to get quantized energies, and we're going to get the shapes of all of the wave functions. But we're going to have to add a step, so it'll be Schrodinger plus probability. That is, we're going to have to go at the end, after finishing all of the Schrodinger equation solving, we're going to have to enforce that the wave functions can represent probability. That is, we're going to have to also normalize. So solving the Schrodinger equation actually doesn't give us normalized wave functions. We have to do that separately because it's kind of a separate issue, a separate interpretation. Okay, so these things 1, 2, and 3 are all going to come from the Schrodinger equation solution plus normalization. So that's a separate thing we have to do. And then once we have these things, then you can do stuff with calculating probabilities. What's the probability of discovering the particle between this place and this other place? Or what's the expectation value on the square of the momentum? Or things like that. Those kinds of questions you can ask the wave functions, but in order to get the wave functions, you have to solve the Schrodinger equation. Also, though, we're going to get all the possible energy level transitions, because these are the transitions simply between the various quantum states of our quantum system. So let's solve the Schrodinger equation problem, right? So remember that our problem looks like this. We have a Schrodinger equation. It's minus h bar squared over 2m d squared psi by dx squared. Psi is psi of x, but just to keep the writing clean, I'm not going to put the dependence on x. It's plus u, the potential energy, is also a function of x, but I'm just to keep it clean, I'm going to not put the x dependence explicitly. You just know that it's there. And then it's equal to the energies, or the energy times psi, where the energy itself is not a function of space. But psi is a function of space, u is a function of space. But also h bar, m, and 2, right? Those are not functions of space. Those are constants. Okay, and our function u, actually let me put the dependence, is equal to 0 for x between 0 and L, and we can put the equal signs there, and u of x equals to positive infinity. It's important that it's positive everywhere else. Okay, so here is our problem. So it's piecewise defined. Let's do the following thing. So I actually forgot to draw you a graph of the potential energy in the previous video. So let's do it now. I'll do it so I'll draw the axes in red. So the vertical axis is the x-dependent potential energy, and the horizontal axis is the entirety of the x-axis. And our potential energy, I'll draw it in black, is at x equals to 0. It just goes all the way up to infinity. Between 0 and x equals to L, it's u equals to 0. And then at L, it goes right back up to infinity. And so this is kind of weird, but I'm going to go and say that this is one of the forbidden zones, and we'll call it region 3. This is another forbidden zone. We'll call it region 1. It's forbidden, remember, because at the boundaries you get these infinite forces. And then in the interval 0 to L, where the particle, the particle exists, let's call that region 2. Right, so these regions, and what's interesting about claiming these regions is Schrodinger's equation is going to be different in the different regions. In region 1, we know we cannot find the particle. What this means is, in a probability way of thinking about stuff, the wave function from region 1 starred, is a function of x multiplied by psi from region 1. So this is the wave function from the forbidden region on the negative side of x equals to 0. This, is the probability density, right, as a function of x, and it simply has to be 0. And so what we're going to say is the wave function from region 1 is 0 because we cannot find the particle there. Also, the wave function from region 3 must also be 0 by the same argument. We're not allowed to find the particle there. Right? So we're going to say that the wave function in 3 is 0, and the wave function in 1 is 0. But the wave function in region 2, we expect it not to be 0 because we know the particle is there. So now our problem is simply to figure out what is the wave function in region 2. And we just need to use Schrodinger's equation, but only in region 2, right? So here's Schrodinger equation. We're going to use it in region 2. In region 2, the wave functions are the region 2 wave functions. The energy is not regional because remember, the energy is not space dependent. It's not a regionally dependent thing because it's not x dependent. So it's just itself. Leave it there. Don't bother it. But the potential energy is regional because it is a function of space, and the wave function is a function of space, right? H bar squared over 2m with the minus sign, none of this is regional, so you just leave it there, right? So the simple thing about the infinite square well, though, is that the potential energy in region 2 is just 0 for all x. So it's a constant thing, but it's regionally dependent. And so we get in region 2, we get the problem minus h bar squared over 2m d squared psi by dx squared plus u times psi, but u is 0, is equal to e times psi in region 2. Oops. Right? So I'm going to simplify this a little bit. D squared psi by dx squared. The result of taking two derivatives of this function is you get the function back, but multiplied by minus 2me over h bar squared. And this is a simple differential equation. And the solutions, right? Solutions are psi sub 2 as a function of x could be a sine kx plus b cosine kx. So a and b are just arbitrary constants, right? I'm sort of invoking the mathematics of solving differential equations. So a and b actually do not depend on x. They are constants with respect to x. And k is equal to the square root of 2me over h bar squared. It's the square root of everything in front of our wave function in the differential equation except for the minus sign. So the minus sign is there because that's what you get if you take two derivatives, right? So check it out. So if I take one derivative of psi sub 2, what I'm going to get is I'll get a cosine kx times k plus, and then when you take the derivative of cosine, it actually gives you a minus sign. So it goes minus, let me do minus b times k times the sine of kx. And then if I take the second derivative, right, so I'll just take another derivative now. I'm going to pop out from the first term here, I'll pop out a k, but now the cosine becomes a negative sign, so I get the minus sign. So what I'm going to do is I'm going to move, I should have done this before, but you get another factor of k, you get a minus sign, and then you get a cosine kx, sine kx. Right, so cosine goes to sine when you take another derivative, and over here sine becomes cosine without another minus sign, right? So the our minus sign that showed up in the first derivative just sticks around, and we get minus k squared cosine kx times b, right? So the b is still there. So what's interesting about this is if you collect terms, or that is factor out the common factor of minus k squared, you get minus k squared times, look at what's left over, it's just psi sub 2 of x. So what I just showed you is, in fact, this is a solution where this is the value of k, right? It just stuck out negative k squared psi sub 2, right? So that means that this is an answer. This is our answer. But there are so-called boundary conditions. One of them that's really important is psi is continuous, right? So the wave function is continuous. What does this mean? It means that psi from region 1 at x equals to 0 is equal to psi from region 2 at x equals to 0. So psi from region 1 at x equals to 0 equals psi from region 2 at x equals to 0. So what was this? This was 0. We argued it because actually just psi is 0 everywhere on its region because we understood the particle not to be able to be found in the forbidden places because the infinite forces would always kick them back into the interval. So, right? So psi 1 of x equals to 0. So the region 1 wave function is just 0. And the region 2 wave function must share the same value. So let's look at our function. So psi 2 of x equals, so a sine kx plus b cosine kx. All right. And then what is the value of the region 2 wave function at 0? It's equal to, this term just spits out 0. But this term, the cosine of 0 is actually 1. So because of the boundary condition, we have to have that the region 2 wave function matches up with the region 1 wave function at their boundary. At their boundary, the wave functions have to be 0. So this implies that we cannot have a cosine part of the wave function. So now, we've actually got sort of a big sort of committing statement. We now know, because of the boundary condition, that the wave function can only look like this. There's no more cosine term. That cosine term is impossible because of the continuity condition. So what's interesting about this is it tells us that we cannot have a cosine shape in our wave function in region 2. So let me show you something really cool. The other boundary is at x equals to L, where we say that the region 2 wave function at L has to be the same value as the region 3 wave function at L, right? But the region 3 wave function at L is actually 0, right? Because the region 3 wave function, it's just the wave function over here. It's 0 at all of its locations there, right? So continuity at the other boundary implies that it must be that if I evaluate the region 2 wave function at the right end, right, x equals to L, then it's got to strictly just be 0. So what this implies is a times the sine of kx equals, a times the sine of k times x equals to L, right, KL, has to be 0. So there's two solutions, or there's sort of one thing you could do is a equal to 0. This one is, let's not go there, right? Don't set a equals to 0, because if you do, right, what this does is it implies that psi is equal to 0 everywhere. There actually is no particle. But that's not true, right? So we can't choose the a equals to 0. Instead, what we choose to do is we say instead that sine of k times L needs to be 0, and a is definitely not 0, right? So the solution is to figure out, what does this imply? And this implies quantized energies, actually. So this boundary condition, when we're solving the Schrodinger equation, the boundary condition itself is going to quantize the energy. And that's actually really, really cool. So implies the quantized energies happen because of the continuity condition, the boundary condition of continuity between region 2 and region 3. So here's how this is going to happen. So the sine of any angle, right? So the arguments of sines and cosines and tangents, really they're meant to be angles. They're not just pure numbers, but they're sort of implied angles. So this is equal to 0 if phi is equal to 0 plus or minus pi plus or minus 2 pi plus or minus 3 pi, right? So the answer is going to be that k times L, which is what I'm saying is sitting as the argument to the sine function, must be, so k times L has to be an either 0 or an integer multiple of pi. So this turns out to be that this k times L, in order to satisfy the boundary condition, k times L must be 0 or n times pi, where n equals plus or minus 1, plus or minus 2, plus or minus 3, etc. All right, so let's go on, and I'm going to sort of make some arguments / pull some fast ones. Can n equal to 0? Let's say no, and that's because if n equals to 0, the wave function in region 2 as a function of x equals 0, and again, we have no particle. So let's not allow, just on physics grounds, like on the choice to still have a particle in existence, there is no such thing as the n equals to 0 quantum number. What about the plus and the minus? Turns out that sine of an angle phi is odd in that angle. That is, if you evaluate the sine of the opposite value instead, it's always opposite to the sine of the value. So the sine function is odd, and the choice of either having phi be a positive integer times pi or being a negative integer times pi, the result is it's only ever going to give you either a 1 or a minus 1 out front. And in terms of normalization, there is no difference between plus or minus n, which means there's no physical difference. That is, having the angle phi, or the value of k times L, be positive 2 pi versus negative 2 pi, you cannot tell the difference physically. So they imply the same. They're actually the same. So let's, just choose n equals to 1, 2, 3, etc. So if you follow along, what this means is k times L is equal to an integer multiple of pi, where the integers are not 0, but only 1, 2, 3, and above. Remember that k was the square root of 2me over L. Oh, not L, excuse me, over h bar squared, like this. So that means that the k times L has to be the square root of 2me over h bar squared times L. And these have to be n times pi. And what this implies is, let's take this thing right here and solve for E. And what you're going to get is E is equal to, let's see, I wrote it down on my piece of paper over here. So E is equal to n squared pi squared h bar squared divided by 2ml squared. And h bar is a constant, pi is a constant, 2 is a constant, the mass of the particles a constant, the interval length is constant, not allowed to vary in time or space. So the only thing that the energy seems to depend on is the integer n. So let's label it with E sub n. And now the wave functions, so if E sub n, right, if the energy is labeled by n, then this thing called k is now also labeled by n, right? Actually, k sub n is n pi over L, right? You just get it from up here. So, yeah, so I've got these really interesting things to say. And now, if I write down the region 2 wave function, it's equal to some constant a times the sine of k sub n times x. So that means the wave functions themselves are not only x dependent, but also index n dependent. So in general, actually, the normalization constant, or this independent constant a sub n, is also possibly n dependent. It also might be labeled by n. It turns out, though, that normalization is a sub n is the square root of 2 divided by L, so independent of n. Yeah. So the wave functions psi of x are piecewise defined. They are in region 1, it's equal to 0 for x less than 0. In region 2, it's actually labeled by an index n. It's equal to the square root of 2 over L times the sine of k sub n x, where the k sub n are given by this thing, n pi over L, right? And then the wave function in region 3, the third piece, is again 0 for x being bigger than L. So this is valid in between 0 and L. Yeah, so the wave functions actually are indexed overall by index n, like that. And then the energies are the E sub n, which I wrote down up here, n squared pi squared h bar squared over 2ml squared, n squared pi squared h bar squared over 2ml squared. Yeah. So the normalization, remember, you get from taking the wave function, imagining the complex conjugate, multiplying by psi of x dx, integrating for over all the possible values that x could take, negative infinity to infinity, and it must be equal to 1. And that will give you this normalization constant. That's just a straightforward integration problem. So I'm going to leave it to you, or you could ask me about it if you're in my class. You could also read about it in a book. It's sort of just a 2-line thing to do. It's very instructive to do it, actually. Okay, so let me just quickly say we've gotten the wave function. It became piecewise defined because the Schrodinger equation was different in different regions. We used boundary conditions. One of the boundary conditions actually told us that a large possible piece to the wave function was actually not possible. We could not have a cosine part because it didn't obey the boundary condition. But when we were solving this problem and went to the other boundary, we didn't get another coefficient to go to 0. It actually gave us the quantum condition on the energies. So that's really cool, right? The other boundary condition did something different for us. And then normalization, right? This step right here, which actually Schrodinger's equation doesn't do for us. We have to go and do that last. The normalization condition gave us the prefactor. It gave us the way to understand the wave functions as being statistical statements. So let's review what I told you we would end up doing. When we solve the particle in a box problem, we're going to have normalized wave functions. And we got those. They were indexed by an integer n, and we made all kinds of physics arguments on why the values of n could only be 1, 2, 3, and so on and so forth. Could not be 0, and we chose to simply ignore the negatives. And then we also got the quantized energies, right? After we did all this, including the normalization, now we can do other things with the wave functions, right? Which you, if you're in my class, you would have learned about actually first. You would have learned that you could study Heisenberg's uncertainty principle and standard deviations as the uncertainties, which are themselves expectation values, right? They're all gotten from making statistical statements about using the wave functions, right? So the wave functions have a statistical meaning, but the wave functions themselves come from Schrodinger's equation. All right, so yeah, in the next video, which will be a short video, I'm going to just draw a few more pictures and talk through this particle in a box problem, or the physics of the particle in a box conceptually.